Hi again. In this video, we're going to do another example of a sampling distribution, and let's see what type of example this is. Okay, so bills at a given restaurant, bills or checks, the amount, have an assumed population mean of $32.40 per person and a population standard deviation of $8.16 per person. Okay, so I'm just going to label as I go, or you could, might need to read it through a couple times. So this is our mu, and this is our sigma. The bills, and that we're talking per person, are heavily skewed to the right. Okay, so if I just draw a little sample, not sample, but a little sketch of our population, it's skewed to the right. So I'm going to have a longer tail to the right, okay? So that means more people are going to spend a regular amount, and then a few people might spend, get a really fancy thing or a bottle of wine or cocktails or whatever. Okay, so it kind of makes sense that this would be skewed to the right. This question says, explain why you cannot determine that a given bill will be at least $35 per person. Okay, remember, I'm just looking for my last page. Remember the one we just did with the pennies? With the pennies, we could do a single individual, a graph for individuals and a distribution for individuals. That's because they told us it followed a normal distribution, right? So I might want to make a note on top of this page that this is when the population is normal. And I put that in the title of that video. Okay, so this is the case. This is how you do it when the population is normal. In this case, we don't have that, right? They're telling us the population is skewed to the right. So this is for an example for theoretical sampling distribution when the population isn't normal, okay? So we don't have a formula for this, right? There are some skewed distributions, but we don't have a specific distribution for this one. So we can't do just one, right? Okay, so I'm going to say the population is skewed . So we don't have a formula to calculate a probability for an individual bill. Individual bill, okay, or a single bill. Okay, other ways to say that, but that's one way. Okay, next question is, can you estimate the probability that the next 5 bills will average at least $35 per person? Discuss each of the conditions for using the sampling distribution of the mean. Okay, so conditions, sampling distribution of the mean. Okay, so conditions, that should register. There's 4 conditions, right? And I've got my conditions and models right here. We've got our first 3 that apply to both means and proportions. And I think we're still doing a mean. Let's double check. The next 5 bills will average, yes. So we will be talking about X bar. This is an average. It doesn't say proportion, right? And it's a numerical thing. So we'll be doing our sample size in addition to these 3 conditions, okay? So think about whether 5 meets our sample size condition. Okay, we got to do all the conditions anyway. So let's just start with number 1. That is independence. Okay, so we need the bills to be independent of each other, right? The bills must be independent of each other in the amount, or in terms of the amount, because we're talking about the amount of the bill, okay? So let's think about a restaurant, and this is a per person bill. So what would influence? Like if folks were sitting at the same table, that might, they would influence each other, right? Like, don't you always go like, hey, what are you gonna get? What are you gonna get? I do. Or if, you know, if they get appetizers, they might split that. So that would make the per person bill higher, right? Or dessert or whatever, bottle of wine, whatever. So I would think these bills could not be from the same table, because those would, each table is going to influence each other. And then you might have a table that's like, oh, let's just share an entree, right? That's going to, you know, trying to stay within budget. So that would be a completely different situation, and they would definitely be influencing each other. Now, sometimes you get those friends where they like order the whole menu and you're trying to have just a salad. That's a whole different situation. But I would think that in order to be independent, these bills should come from different tables, and they should be randomly chosen, right? Okay, so I'm going to say the bills should come from different tables. Okay, I'll get the random sample in the next one, and maybe you take, you know, maybe you're taking the next 5 bills, you know, where each one's a table, and you're taking one from each table. That could work. Also, if there's a large group that maybe had multiple tables, that would also be another sort of not independent situation. Okay, so randomization. So these are all things we need to be thinking about as we're setting up a study, and with the intention of using a model like this. Randomization. Okay, the bills must be randomly selected. Okay, so this next 5 is kind of a problem, rather than, so I'm going to say randomly selected rather than in a row, or you could say successive. Okay, so we should randomly select the bills. Okay, the next one is the large population. I'm looking at my notes here. Large population. Okay, so all the bills must be more than 10 times, and we're saying 5. I'm going to say the population of bills must be 10 times the sample size. Okay, so if we used 5, we would need 50, right? Which seems like no problem. Like, let's say in an evening, a restaurant serves at least 50 tables. I don't know exactly. If you have experience with that, you might know better than I do. But I want to do sample size first, and I bet you can guess why. So for a mean, sample size is the next one, and this is our second of the 2 cases, right? So the first one is if the population is normally distributed, even small sample sizes will have a normal shape. So any sample size is fine, but we're not in that case. We're in the not normal population. So the sample size has to be 30 or larger. So the 5 is not going to work, is it? So the population is skewed. So we need n greater than or equal to 30. So we need at least 30 random bills in order to get a normal model, okay? Okay, so that was a long way of answering this question, although it does say discuss each of the conditions, which we will have to do each time. So somewhere I'm going to answer this. The next 5 bills would not work, right? Because 5 doesn't meet the sample size of 30. But the part C says if we take a random sample of 50 bills from a month, would all the conditions be met? And in that case, I would say yes, right? Because if we did 50, that's more than 30. And also, then we would need our population to be 500 or more, right? So as long as that was in a month, and it seems like it would be, depends on the restaurant, though, of course, we should double check that. If it's a really, really small, it might not work. We've got to just answer this for the 5 and for the 50, okay? So I'm going to say a sample size of 5 will not work. Of 5 is too small. Okay, but for 50, I'm going to say yes, as long as the population is 10 times 50, 500 or more bills. Okay, so I went back up to the large population for 50. It definitely would work for the 5, but the 5 doesn't meet the sample size, so it's got to be big enough, but not too big. Right? Okay, so yes, so we've got that one. If we take this, would all be met, so I actually had more space to write that one. Now we get to go to our sampling distribution. Define, draw, and label. Sampling distribution model for the per person average of 50 bills, okay? Okay, so remember we already have a per person, but now we're taking the average of 50 bills per person. Okay, so define. So I got to get my model again. So here's my conditions and models page, and this is the formula I'm going to use because we're doing X bar. We have a mean, we have a standard deviation, and we have an N, okay? So I'll write out the general formula first. X bar is distributed as normal with a mean of mu and a standard deviation of sigma over square root of n. Okay, now I can fill in my numbers. So X bar is normal. Remember, because we've met the conditions, so even though our population was skewed, we've met the conditions, so we do have a normal curve for our average of 50. And the mean will be the same as the population mean, even if it doesn't start normal. So 30 to 40, comma, I'll show you where I'm getting that from. That's from our original population mean. And our population standard deviation is $8.16. So we have $8.16 over the square root of what's the sample size? Okay, if you said 50, you're right, because we're doing 50 bills. So that's our N. Okay, so let's calculate our new standard deviation. Oops, I cleared my memory. Great. 8.16 divided by, 8.16 divided by square root 50. 1.15, and this is money, right? I probably will just keep 4 decimal places, but this is money, so it's like $1.15 is our standard deviation. I'm just gonna keep 4 decimal places to keep it more accurate. 1.15399, so 1540. 1540. 1.1540, yeah, the 9 rounds of 39 up to 40. And this is dollars, right? If it helps you put your dollar symbols in there. We'll label our graph though. Okay, so let's label our model. And now you could put this into Staplet if you want. I'm going to draw it since I don't have it pre-printed on here. Put a tick mark for the mean in the middle. 1, 2, 3, 1, 2, 3. I've got my normal curve like that. 32.40 in the middle. I'm also kind of drawing this as wide as I can. I wish I had drawn it a little bit wider because I've got dollars and cents, so it's going to be, I'm going to have to squeeze this in here. So now I'm going over to Staplet, and 32.40 is our mean. Our standard deviation is 1.1540. Okay, and now I've got my graph, 32.4. I'm going to get my labels off of here. 33.55. And I'm just going to do cents for my hand drawing. 34.71, 35.86. Going down from the mean, 31.2, 30.09, and 28.94. Okay, let me show you what I did. So now I've got my labels. So our graph, 3 standard deviations away from the mean goes from about $28.94 to $35.86. Okay, so, and that's our sample to sample variation, right? So let's write our label. So we have the average per person bill from 50 bills, or average, yeah, I think that's how I'm going to say it. Average per person or average of 50 per person bills. Might have been a little bit better. Average per person bill for 50 bills. Okay, in dollars. Okay, got to get our units in there. Okay, now we have 2 questions to answer from here. E is, how likely is it that a random sample of 50 bills will average at least $35 per person? So let me find my $35. It's somewhere in between these two. So it looks like we'll have some probability, some non-zero probability there. Let's go back to Staplet. So at least, I'll write my probability statement first. Probability that X bar is greater than or equal to $35. So now we're going to the right. 35, calculate area. And remember that the equal sign, whether it has the equal or not, doesn't change the value mathematically, because there's no, if for a single value, there's no width of a rectangle, so there's no area to a single value. So it said at least, which in real life would mean 35 or greater, but also if it said greater than 35, it would be the same numerical answer. Okay, so our area of that is 0.0121. 0.0121. Okay, so pretty small chance that the average of 50 would be more than $35. Now let's look at a different question. Find the cutoff values for the middle 50% of the mean price per person for 50 bills. Okay, so mean price, average price. It's just another way of saying it, right? So middle 50%. So this is, we're going to be finding our cutoff values. Okay, so now we're finding cutoff values. This one, how likely is a probability, right? So this is good because now we get to practice our inverse normal. So I'm going to go back up to the very top and change the operation on Staplet. So calculate a value corresponding to an area. I'm really happy it remembered the mean and the standard deviation. So that's really nice. So it's got our mean and standard deviation, but it's always good to double check that. And then you can hit plot distribution if you need to. And then remember, for this one, our options are left tail, right tail, or central. So middle 50% is central. And we put in our area of 0.50. Okay. You could also think of this as the inner quartile range, right? Because that's also the middle 50%. This, if we subtracted the two values, that would be the inner quartile range. Okay, show labels on plot. So here are the numbers we got: $31.62 and $33.18. So if it's asking for values, I'm going to go ahead and use the units, and because dollars and cents, I'm going to use 2 decimal places. Okay, so then I'm going to write it out, the cutoff values. I'll go back to the notes here. The cutoff values for the middle 50% of the average bill per person, or average of 50 bills per person, are, and now I've got to go back and get my values. $31.62 and $33.18. Okay, let me go back to the notes. Okay, the cutoff values for the middle 50% of the average of 50 bills per person are $31.62 and $33.18. Okay, so I could label that in green to go with this color in my graph up here, 31.62. So that's, remember that one standard deviation is 68%, so the middle 50% should be within the first standard deviation on both sides. Okay, so that's our middle 50%, and we just found those cutoff values, and just, I'll write a note here just to remind yourself, this is the inverse normal. Okay, so instead of asking for a probability, they asked for cutoff values. Okay, so I bet you're seeing, I hope you're seeing that once we determine or make sure that the conditions are met and we get our model, then we can do anything we were doing with the normal model. We can find a probability to the left, right, and center, and we can also find cutoff values and percentiles and anything like that. And we can also do z-scores, just like we were doing before, and Staplet is really nice that it calculates the z-scores for us. And this is, these are the same because it's the middle 50%, right? With symmetry, these are the same z-score, but one's positive and one's negative. Okay, great. So you get to practice this, and I'll see you in the next video.